Good evening, one and all. Let's wait for a couple of minutes for everyone to join. We will start in some time. Uh, Good evening. Let's start with today's class. Am I audible? Today it's only one student. Can you tell me, like, should I discuss a brief of the class or directly go to the assignment because nobody is there? And depending on your queries, we can move forward. Yes, can you tell me? Okay, I will just give you all an overview of what we have been doing, and then we will jump to the assignment. Okay, so far we have been discussing on various type of you know uh, treatment methods used for removing the contaminants from wastewater, which is generated from industry, right? And these uh, amongst these pollution treatment techniques, we have discussed few very common treatment technologies which are generally used in all the industries, including coagulation, flocculation, equalization, sedimentation, right? Filtration. So now, in since the last class, we have been talking about adsorption and its application in industries, right? So in by using these adsorption process, we can basically target some very some pollutants which are not removed by the conventional ones, like activated sludge process, or uh, you know any suspended particles, like suspended particles will be majorly removed through sedimentation, but whatever is not removed, we can try using adsorption. So basically, what is not removed using sedimentation or activated sludge or biological process includes few non biodegradable uh, organics, uh, heavy metals, right? So this include dyes, some other colorants, right? Um, Refractory, even, yeah, sometimes oil and grease. These all pollutants we can remove using adsorption, right? So we have been talking about adsorption, what the process is, and how do we select the adsorption, what are adsorbent, and what are the uh, mechanism of adsorption, and what are the factors that affect in selecting an adsorbent, right? So we have discussed all of this till the last class. Now we will be talking about in industries how do we use the adsorption process. So in industries we basically use a fixed bed column, right? So in a column there will be a support which can be of glass wool or some sand or so, and inside that we pack our adsorbent, right? Now there could be two possible ways of the flow: top to bottom and bottom to top flow. uh, and let's say there is a bed of adsorbent in which it is randomly arranged, or you can use some packing material as well inside to fit, like to have more organized flow of water across your adsorbent, right? So as the water containing the pollutant, it passes, let's say, from top to bottom, it passes through the bed of adsorbent. Like initially you can say all entire adsorbent bed is uh, you know uh, free of the pollutant. So uh, like maximum removal happens, right? So very low concentration, or you can say majority zero concentration is obtained till a certain point, right? So there will be, like, let's say this is the bed of adsorbent, right? So depending on the concentration, there will be a zone in which the adsorption occurs, right? Let's say this is the initial concentration C naught, it reduces to final concentration, let's say 0.001 of any pollutant. It reduces to 0.001 in this much length of the bed only, right? So only this much region is utilized for uh, for this time being, and after that wherever it passes, it just like there is no adsorption taking place. So this you can say as the mass transfer zone, right? So mass transfer zone is the area in which the actual adsorption takes place. Now there will be a certain time when, because the adsorbent has some capacity to adsorb light, so this portion will get like it will tend towards saturation, and this mass transfer zone will keep on moving, right? So let's say it was here, so next it will be here, after some time it can be here, right? So you can ideally you can say the mass transfer is moving, and it moves as if it is like moving, like a wave moves, right? So you can say it's a wave front as well. So basically whatever the adsorption takes place, it happens in that zone only. Now there will be a region where the mass transfer zone, like after that mass transfer zone, the pegged bed has ended. So once that is utilized, you will start seeing the concentration of the pollutant in the outlet also, right? So let's say this is the inlet and this is the outlet. So after some time you will start observing some concentration, right? So whenever you see a rise in the concentration, so that is nothing but the breakthrough time. And breakthrough time is usually dependent on the permissible limit of the pollutant as well. For example, uh, let's say if you have dye in your wastewater, so dye will give color to the wastewater, right? And you want to absorb that dye. So for a good quality water, it should be colorless, right? So what will be the permissible or breakthrough point for your dye containing water? It should be 0 ppm concentration of that dye, right? So as soon as it rises above certain level of 0 ppm or above a level of colorless, you will start seeing like breakthrough has attained, and that time is known as breakthrough time, right? So this time is known as breakthrough time. And after that the concentration keeps on rising until it has like entire bed is saturated, and you can say whatever is going inside, it will come from the outlet, because you can say the bed has saturated, right? So in industries you will be able to use your column until the breakthrough time, because after that the concentration of pollutant is coming out in the outlet which is above the permissible limit, and now you need to stop using that bed. Now the breakthrough time it depends on various factors, right? So breakthrough time, it depends on the length of the or the depth of the bed. Okay, so usually the breakthrough curves are of S shape. Now if uh, the bed is assumed to be the most ideal one, then this steepness will be very high, right? And as the non-ideality increases, you can say the S can have more, you know, this width. This width also, like the spreadness of S curve also depends on the depth, right? For example, and the flow rate also the inlet concentration. For example, if you have lesser depth, it will saturate initial fast, right? Because you have lesser amount of adsorbent packed inside, and hence it will saturate faster. or the breakthrough will be attained faster. Like this is very obvious, right? And here, as you see, this is actual plot of some pollutant being removed, right? So as you increase, keep on increasing the uh, depth of the bed, right? So the breakthrough time is increasing and the S curve is like becoming less steeper, and also the breakthrough time is shifting, right? So more the amount of adsorbent, obviously more will be the breakthrough time. Now again, this breakthrough time depends on the contact time or the residence time which pollutant spends inside the column, right? Or in the fixed bed in contact with the adsorbent, right? So that is nothing but one term for it, which is empty bed contact time, which is a measure of sort of the time spent by pollutant in contact with the adsorbent, right? So more the contact time, more will be the uh, you know uh, time for the pollutant to interact, right? And more will be the efficiency, or more adsorbent will be utilized uh, efficiently. So if you have, let's say, and contact time is inversely proportional to the flow rate, right? So you can say more the flow rate, lesser will be the like earlier will be the breakthrough. So this will be the highest flow rate as compared to this, right? So this way the flow rate reduces, and this way uh, contact time reduces, right? So lesser the contact time, uh, you know you can say the it is not getting enough time to you know interact, and that is why you can say the breakthrough will be earlier, right? Is that clear so far? Okay. Yeah, so moving forward now, these breakthrough curves, they are usually like as we have discussed in the last class, various models for fitting the kinetics and the isotherm. Can somebody tell me why do we need to fit models in any of the experimental data for the removal? Uh, it can be any model, kinetic model or isotherm, any model. Do you know why do we need to fit these models? Yes. Okay, so while deriving these models, अरे यार, Sorry, I got logged out of the meeting. Yeah, so we have been discussing that why is model fitting important, and what insight does it give for any of uh, the removal process. So model fitting will give you while deriving the equations. So there are basically common models available which you can directly use. Uh, so while using those models or while deriving those models, there were certain assumptions made, right? So these assumptions can give you insight on some basic mechanism which is prevailing for your, you know, for your process, right? So likewise, if we want to model breakthrough curves, there are already available models which, depending on the fitting, right, from the r square value, you will get the idea of what is the basic mechanism, and uh, what is the limiting factor behind your uh, experiment or behind your removal process, right? So here in that case, that these models are uh, include Thomas model, Yoon Nelson model, Clark model, etc. And there are many more models which you can use and get more insight of uh, your process. Yeah. So let's move forward. Sorry. So this was all about the adsorption process. Now let's talk about another process which is very much explored in water treatment, and which is used mainly for softening of water. And this process is nothing but ion exchange. So basically, it, as the name suggests, it is the exchange of ions. It could be cation with cation, or it could be anion with anion. And usually it is used for exchanging cations which are present in water, that causes hardness, right? So for example, these cations include calcium mainly, magnesium, right? And to some extent other divalent ions or bivalent ions, uh, which can cause hardness, right? So these ions are exchanged with ion exchange resin, and these ion exchange resins, are nothing but polymeric compound which has functional groups on it. And these functional groups, let's say it has carboxylic functional group. So this hydroxyl functional like COOH, let's say it has. So the hydrogen from this is usually replaced. It can be as it is, or it could be in the form of, let's say, COONA, right? So this is also possible, right? And it is connected to some resin, right? So now this COONA, when it comes in contact with, let's say, hard water containing Ca2 plus, so here the exchange will be such that uh, like 2, because the valency is 2 Ca, right, plus 2 Na will be released from this resin. So this is the reaction which goes on when the ion exchange takes place. Now this the efficiency of this process, it completely depends on the on various factors. And these factors like, it can be the choice of resin, it can be it can be the affinity between the resin and the uh, cation, because you might be targeting various cations, the existing parameters of water, uh, right? So let's say if you have choice of cations, and if like uh, then there are number of types of resins. So strong cation exchange resin is nothing but the one which completely dissociates, and obviously it will have higher efficiency because it has higher dissociation under all the pH conditions, right? And this includes SO3, like any resin which has uh, sulfate ions, right? Or sodium sulfonate, right? Another class of resins are weak cation exchange resins, which are only able to remove carbonate hardness. Now, there is a rule that the salts and any ions, if they are present in water, they are having better affinity or better exchange capability if they are, you know, having like behaviors or like characteristics, right? So for example, weak exchange resins will only be able to remove carbonate hardness, because carbonate hardness are because of the salts which are formed by weak acid base reaction, right? Or you can say weak acids because of carbonates, right? So let's say H2CO3. So this is a weak acid, and the salt because of formed because of reaction involving weak acid. You can say it will be more uh, effective in removing the salts or the hardness corresponding to the weak salts or carbonate hardness, because it contributes from CO3 2 minus or HCO3 minus, right? Uh, Next is the mechanism and the rate governing step for an exchange process. And as we have seen in the adsorption process also, the steps are similar. So first is the movement inside in the bulk to the film, like from the bulk of the solution to the film of the hardness causing cation, right? And once it has reached the film or the boundary layer, it moves inside the boundary layer to the surface of the resin, where it will face some resistance. Now, once it has reached the surface of the resin, this resin could be porous, right? So, if I give you the example of one resin, then zeolites, right? Zeolites are one class of resin which can be used for uh, removal of hardness, right? So zeolites are nothing but porous structures. So since all the resins majorly are porous structures, so diffusion inside the pores also plays an important role in governing the overall rate of the process, and that is nothing but known as internal diffusion, right? Then once it reaches the site where the exchange happens. So here, let's say the fourth step will be the exchange of ions between cation and the sodium ion which is present on the surface, and sometimes it could be between H plus as well, right? It depends on the choice of your basin. And once now, till this point it was for the adsorption, because in adsorption, whatever the pollutant was to be removed, it used to stick on the it used to adhere to the surface of the adsorbent. Now here, what has happened? Exchange has happened, which means that with the resin, the Ca2 plus will attach, and you will release Na plus or H plus in the uh, solution, right? So again, whatever steps were followed going by the ions going inside or going to the surface and to the exchange site, same steps will be followed, right? But in the reverse order, right? So now the Na plus has released, so it will move out of the pores, right? So again, internal diffusion. Now once it has moved out of the pores, it needs to come out of the boundary layer, which means external diffusion it has to overcome. And last is the transfer in the bulk solution, right? So as to have uniform concentration. So all these steps, they govern the rate, and the step which is having the least or the slowest step, it will determine the overall rate of the process, right? So is it clear so far? uh yeah, let's move forward. So similar to adsorption process, ion exchange also resin also has some capacity to exchange ions, because it depends on the amount of Na plus or H plus available with the resin, and it has to exchange with uh, Ca2 plus, right? So here again the exchange happens with different valencies. So whenever you are dealing with ions having different valencies, it is always better to express the concentrations in terms of milli-equivalent per liter or milli-equivalent per gram, right? So when it comes to the capacity of resin, you should express how much milli-equivalents of your hardness can be removed per gram of resin, right? So this is how your ion exchange capacity is uh, expressed. Now, when it comes to uh, the expression of hardness present in water, you should express it as milli equivalents per liter of hardness, right? And since it is hardness, it is always expressed as milli equivalent per liter of calcium carbonate, right? So if you are solving any numerical, or if you are dealing with ion exchange, or if you are dealing with hardness removal, always use milli equivalents as the concentration, right? So milli equivalents per gram for its capacity of ion exchange, or milli equivalents per liter for the hardness concentration, and also it should be in the form of expressed in the form of calcium carbonate hardness, right? Now next comes as the selectivity, and this is but obvious because depending on the cation you want to target, and you are depending on the resin that you are using, uh, all cations and the resin combination might have different interaction and hence different affinity, right? So cations may have varying affinity to the surface, and for that you need to have basic laboratory experiments, and basic thumb rules are also available uh, in the literature from those experiments, which, like, you can say initial lab test. Now various theories are also available, which will provide you with the guidelines to select any resin, right? uh, yeah. And yeah, also the ion exchange uh, rate and also the affinity, it depends on the valency, it depends on the uh, you know the mobility of ions, right? So mobility of ion depends on the radii, right? So mobility of ions, it depends on the radii. And here, since ions are present, this radii will be like all the ions. If they are present in water, it will be hydrated, right? So you can say any ion, it will be surrounded by number of water molecules depending on the ionic radii. and that radii is known as hydrated ionic radii. Uh, and you will find a literature on what are the hydrated ionic radii of various ions, right? So smaller the hydrated ionic radii, you can say smaller dimensions of uh, ions will cause faster mobility, right? And you can say faster exchange might be possible, and the ones which are reaching faster, they will tend to be uh, exchanged faster, right? Next is the ones which are easily polarizable, right? So it should be easily dissociated to ions so that it is able to uh, interact faster. So yeah, and last is the separation factor, which is expressed in terms of alpha, uh, yi by yj by xi by xj, and it's the factor which tells you what is the amount of ions present on the surface of resin as compared to the ions present in aqueous phase, right? So y is for resin phase, x is for aqueous phase, and I and j are two ionic species, right? So yeah, this will give you the distribution of ions on resin as compared to the aqueous phase, right? So more the separation factor, more is the affinity of that cation for that resin, right? You can say that. Yeah, so next is similar to adsorption process. This ion exchange is also performed in a sort of fixed bed ion exchange bed, right? And there could be multiple ways of operating it. So if you talk about ways of operation, so usually what happens in industries, you cannot, like, wastewater is always coming, right? So it is, you cannot let's say the bed has some capacity to absorb or exchange, right? So when the bed is saturated, you cannot say wait, the bed is saturated, so you will have two or more beds always. So while one bed is under operation, another bed will be, let's say this bed was under operation. So once that this has saturated, the wastewater will be sent to another fresh bed, right? So this will be operation, under operation, and this bed will be regenerated during that time, regenerated during that time. So you can say usually the operation is made you know in alternate means, and the flow can be in various ways. So while uh, let's say the wastewater flows in from top to bottom direction, this is the direction of treatment. So if the regeneration also happens from top to bottom, then it is co-current, and if it is in reverse direction, let's say this is the treatment, this is the regeneration, then it is counter current, right? So co-current is usually easier to operate and low cost. So but what happens to counter current, it is always giving you more efficiency as compared to co-current, right? But it is somewhat difficult to operate, and you need uh, higher sophistication and more expense to deal with that sophistication. Now why co-current or counter current is always better, because counter current, let me give you an example. So let's say this is the trend, any trend if we are following. So this is the concentration profile which is followed. So uh, for counter current, you will say, when if this is the inlet point where for the regeneration, it is coming in contact with the sorry, I am doing something not relevant. Yeah, let's say here, for your column, this is the concentration profile where it has reached high, you know, it is coming out as high concentrations already. So if you are giving like this, from this end, from the other end, you will say, it will, there are chances that maximum interaction happens, and that is why, like, in during this mode, you will be contacting, I'm not getting the words to explain. You will be contacting the uh, you know least utilized region through the maximum, you know maximum available exchange possible, right? So for example, near the end of the column, this zone will be least used, right? And that zone is coming in contact with the fresh regenerating solution, which has maximum, right? So here it will be uh, some mass transfer gradient, and that mass transfer gradient will be prevailing throughout the column, right? So that is why you can say the efficiency is maintained throughout the column, which is not in the case of co-current. So what happens in co-current, the maximum, the least, like the fresh regenerating solution, it goes inside the column where the bed is maximum saturated, right? So bed is most utilized, and and there at that point you will have the highest, the mass transfer gradient, and that mass transfer gradient, it reduces when it comes to the end of column, because there not only the regenerating solution is used, but the bed is also less saturated, right? So you can say, uh, since the driving force is maintained throughout, the efficiency improves always, and in that case you can say you will have higher quality of water. Chemical consumption is also minimized. Now if you want to put a balance, yeah, so is it clear so far before I move forward? I hope so, like nobody is responding. Yeah, so this is what we have been discussing on why we need multiple columns, and behind that multiple column strategy, there are a number of possible ways where you can arrange your columns. One is standby columns. So standby column, as the name suggests, you have one standby column or backup column which you can use when you have some issue, or when uh, you have uh, you know uh, some maintenance required or some failure happened, right? Another is possible combination is in series, where you use three columns uh, arranged. So So the most used column, or the ion exchange column, will be, let's say this is the first column which is used. So once this is saturated, this will go under regeneration and second column will be used. Once second column is used up, it will, the treatment will be passed on to, or the ion exchange column will be passed on to the third one, and this will be under regeneration and so on. So this will go as if like it will go around in a complete cycle, right? And last is the parallel, where you are dividing the wastewater stream into three different columns, right? And you can say you are bypassing also. So this is how it works. Next is the resin selection. So resin selection, for this you need some basic lab experiments, and this resin selection depends on the capacity of the resin for that particular cation, right? So this is the basic or the primary selection criteria which will be used for all the cases. And as we have seen in the adsorption also, similar terminologies are here as well. EBCT, which is nothing but empty bed contact time, which is the ratio of the resin bed volume, right? So which is obtained by mass of resin used into the density of the resin, which is equals to volume of the resin divided by the flow rate, right? And the SFR, which will be the ratio of bed volumes of water uh, produced per hour, which can also be obtained by flow rate per unit uh, volume of resin, right? uh, yeah, you always estimate how, before actually going to an act using or to the industrial scale, you perform pilots lab tests and the pilot scale test, where you estimate what will be the amount of resin required and what will be the amount of volume treated, right? So for industries you always know. So how do you start from lab? First, you similar to adsorption, you generate a breakthrough curve, because this resin also has some capacity. So you will know how much amount of volume can be, uh, you know, uh, treated, or this applies for both an exchange and for adsorption. Uh, Treated or softened by using unit weight of resin or adsorbent, right? So once you have find out this, now you can scale up. For industries, you from this you know how much amount of volume can be treated, and now in industries you know the volumetric flow rate, which means you know how much amount of volume you need to treat per unit time, and how much amount of volume you need to treat, and you have some basic considerations of cost and the land, and depending on that you optimize the size of your column and the resin or the adsorbent that you will be using for that particular flow rate here, right? So uh, that is how you estimate the amount of uh, the ion exchange resin you use. And obviously the regeneration happens by using, for example, you want to have reverse reaction, right? So earlier what was the reaction? Resin which had Na plus, it was contacted with hard water, and Ca2 plus replaced Na plus, right? So now you have, for regeneration you want to remove Ca2 plus, so you need Na plus solution, which is supposed to have very high concentration, right? So such solution will be nothing but brine solution, right? So you use around 5 to 10% of brine solution for regenerating your ion exchange resin. Is it clear so far? So will t- I will take a minute and I will come back in a few minutes. Please give me a moment. Let's move forward. Yeah, and if we talk about the major and the real consideration, so it could be piping consideration, the disposal of the used resin, the disposal of, if you talk about adsorption, then disposal of used adsorbent, disposal of the regenerating solution, or here in case of ion exchange, the brine solution, right? So brine solutions are usually disposed of in sanitary sewers, or you can say oceans, because ocean is nothing but a very high concentration of salt it has, or some deep well injection. You inject it inside uh, uh, well, or uh, you know inside the earth. So this is how you do. And yeah, so do you have any doubts, or we can move to the assignment? Okay, let's move to assignment. uh First question is, which term will be obtained when proportional amount of adsorbent actually involved in sorption is divided by the total amount of adsorbent utilized for the mass transfer zone. Okay, so here the answer is fractional capacity, because the key term here is, you see, you are focusing on the proportional amount of adsorbent used, right? So which is the actual, or actually, uh, uh, if the ion exchange resin has some capacity, there are chances that not totally it will be used. So fractional capacity is the correct answer here. Next question is, height of the mass transfer zone is the area where practically all the dash takes place. So here, mass transfer zone comes into picture for two cases: adsorption or ion exchange, right? So here, you see which option applies here. The correct answer is sorption, right? So option B is the correct answer. Clear so far? Okay, so here the next question is, the weak cation exchange resins can remove dash hardness. Sorry, somebody was speaking. Yeah, so it weak cation exchange resin, it can remove uh, carbonate hardness, right? Because as we have discussed, it's sort of you know like I have already explained why it can remove only carbonate, or it is more efficient for carbonate hardness. Uh, Next is, unexchanged resins have a variable preference or affinity for the ions in solution, and this preference or affinity is called as dash. It is termed as selectivity, right? So how much selective is for one cation over the other cations if they are present, right? So your ion exchange resin should be selective for the ones you want to target. Next is, in ion exchange setup, merry-go-round is known for dash. So it's for columns in series, right? Because one after the other, the column is used in the cyclic process, and the one which is utilized, it goes under regeneration, and it goes one by one in a cyclic mode, which is also hence known as merry-go-round setup, right? Next question is which model used the mass transfer concept in combination with Frunlich isotherm to define a new relation for breakthrough curve. So what is it? So that is nothing but Clark model. As we have discussed that all these models have some basic assumptions made while deriving those you know models. So for example, Thomas model was derived while taking into consideration monolayer adsorption along with pseudo second order kinetics taking place, and uh, later it was derived for continuous removal, right? So these Frundlich model, Langmuir isotherm, they are for batch experiments, they are derived from batch experiments, while for continuous removal where we derive breakthrough curves, you choose some of the hypothesis from your uh, batch as well, which gives you uh, Clark model here. So for Clark model, Frunlich isotherm was the basis. Next question is a factor which measures the preference of one ion for other ion is known as binary separation, right? Next question is in the dash, the outlet concentration remains near zero until mass transfer zone starts to reach the tower outlet. So it's a breakthrough concentration profile, right? So this I have already explained. When the mass transfer zone reaches the reaches the end of the tower, the concentration of the pollutant or uh, the concentration starts coming out of the column, like it starts rising, and that point or that curve is nothing but breakthrough profile. Next question is which factor measures the preference of one ion over the other? Yeah, binary separation factor. Again, the question has repeated. A flow of water is introduced through the under drain is known as dash. It's backwash, right? So I guess I have not discussed on backwash. Can you tell me what is backwash and why it is required? Yeah, so backwash is usually provided by using uh, or by flowing water, and usually in counter current mode where the bed is allowed to expand so that if any suspended particles or some solids they are stuck, it will be washed away, right? So if the bed is expanding, suspended particles are will also be washed away by that water, right? So backwash is important. So that's it from my side. Do you have any more doubts? You can let me know. Okay, so you can check for your doubts. I will be around for a while. Uh, if you have any more doubts, you can do let me know. So, do you have any more doubts, or should I end the class? Okay, so if not, I assume you don't have any more doubts. I will end this class here. Thank you everyone for joining. We will meet in the next class next Tuesday. Thank you.